All right. Welcome everybody to the joint CEDAR jam session, the Mesos focus group, to the electrodynamic coupling of thermosphere, ionosphere, and magnetosphere from high to low latitudes. Actually, since we are not a very big crowd, if you guys can come closer to here, sit closer, that would be better. I just want to remind everybody that this is the session schedule that we have. We're about like 12 presenters today. So everybody has 10 minutes set for a highlight presentation. From the CEDAR student representative and a couple 8 minutes presentations as well. Please also let's keep our 10 minutes talks to about 8 minutes or so we can have like at least one question for discussion. And remember to bring a brief comment on how a collaboration with a CEDAR or GEM researcher can actually help you to advance in your research and your studies. Okay, thank you everybody for coming. Please welcome Daniel Bullet with the presentation and revealing Mesos versus large-scale dynamics using ground and space-based observations. Where is the, oh, sorry. Okay.
I can do the slides, don't worry.
Okay, yeah, thanks for having me in this. So this, something I thought about for a long time is the concept of kind of like scales. You got large scale stuff, there's mesoscale stuff and small scale stuff, and it's all kind of very confusing, and it's hard to kind of tell where the line between them sits. And sometimes you can get like small scale stuff embedded in mesoscale and large scale features, so it just kind of gets all a bit blurry. So this is kind of like a small study that was done a couple years ago, but it's something I'm very proud of because I think the results are like very nice and clean, and it just kind of like got me thinking about scales and kind of like how we think about them. So firstly, kind of I want to introduce the large-scale system that I'm very, very familiar with. You could call it the quasi-static system or DC or big picture. Basically, I'm just talking about, the very old and classic field line currents coming in, connected to the convection pattern, and that drives this, fairly large-scale pattern, which I'm very familiar with and a lot of other people are very familiar with. But the caveat here is this is quasi-static. So by quasi-static, I mean that all these large-scale processes are all connected to each other, and basically the same thing. The convection is basically the same thing as the field line currents because you can't have one without the other. The DC electric field, etc. So if we wanted to work out the Poynting flux in that scenario, so the total electromagnetic energy transfer between the magnetosphere and the ionosphere, it's actually extremely simple. You can take a convection pattern from something like Superdon or an electric field from a model or something like that, and you could take magnetic field measurements, any will do. So I've used ampere in this scenario just to kind of match the same vibe as Superdon, and you can just plug that straight into Poynting's theorem, and you can derive the Poynting flux, and then you can wash your hands of that. Good job, we finished it. We solved the amount of energy coming in. Well, that's great because it gives you this Poynting flux pattern, and you can, that's if you use Superdon and ampere, that's great because they have temporal cadences of 2 minutes, so you can get a global Poynting flux pattern every 2 minutes and figure out where all the energy is coming in. But that's large scale, and we know that large scale kind of like underestimates on, spatial and temporal scales to some degrees. So what do the lower scales look like? Well, that's a really good question because I still don't know the answer to this, and I don't know where to draw that line. So let's kind of like take a step back and say, okay, Superdon and ampere, I know that's big, right? So let me start by putting a barrier right there and saying anything smaller than that, that's mesoscale and that's small scale. So this is where, for this study, this is where SWARM came in, or you could use kind of like any satellite basically flying through, like DMSP would work equally as well. SWARM has an electric field instrument, has a magnetometer, so you can also plug that into Poynting's theorem, and you can work out Poynting flux from it. Is my mouse going to show up here? Yeah. So the top line is just this gray in the background is just the raw electric field, 16 hertz. It's quite high temporal resolution. Electric field measurements from SWARM, can't remember, B, I think in this case. And then what I've done is overlain over the top of that. It's just a smoothed out curve at various different spatial scale sizes. That's just using a low pass filter to kind of smooth it out to larger temporal scale sizes. So you can see that there's like, there's some noise in here, but there's also some decent amount of temporal variability that we're not sure what's what. It's kind of hard to see, but then smoothed out, you can envision this looking like something that SuperDARM would measure. And then when you work out the Poynting flux, which is this one, and then you can do this thing which I've done a couple of times, which I think is really useful. You can work out the cumulative time-integrated Poynting flux. So you can work out how much Poynting flux is coming in, like overall, in the amount of joules coming in over a period of time. And if you do that for this piece of data that I've got here, the gray is just the straight underlying 16 hertz data. But then these colored lines, those are those smoothed out lines. What you find is the smoother your data set, the less and less Poynting flux you're actually measuring overall. So what that's telling you is if you have low spatial resolution data, you underestimate the Poynting flux, which everyone kind of appreciates that you're a high time resolution or high spatial resolution, you get to see more variability, and it's been conceived over time that there should be more joule heating and Poynting flux in there. Well, here's just the straight proof that that is the case. And another thing is if you look at Poynting flux statistically, which are these two plots, the one on the left is doing statistical Poynting flux with SuperDARM and Ampere, and the one on the right is with SWARM, just the SWARM data. Well, then it doesn't take a lot to see that these don't look very close to each other. So what's going on here? Let's look at some case studies. This is a case study, so each of these panels is 2 minutes in length. It's a SuperDARM convection map timescale. And I've kind of then put the SWARM data on the bottom, and I've overlain that with the SuperDARM and or Ampere data in black. So the red, or the middle panel is your electric field. And I've also then divided this into SWARM data that I've tried to smooth out into larger scales. So the blue line is me smoothing out the SWARM data to make it look like SuperDARM, for example, for the electric field, and then for the bottom, doing the same to make SWARM look like Ampere for the magnetic field. And that's basically smoothing out and say, okay, let me make some large-scale data out of this, very noisy and variable electric field and magnetic field data. So I've done that in the middle and bottom panels, and that's the blue and black lines for both of those. And then the red line is just the residual, whatever's left over from after I did that smoothing. And yeah, you can see I can actually get the SWARM data to look pretty close to SuperDARM at least. That's the black and blue line in the middle panel, and then fairly close to what Ampere sees in the bottom. But then there's all this variability going around. So that's all the stuff that SuperDARM and Ampere is missing. So that's, I guess, the everything else scale in everything I'm talking about here. And then here's another cool situation. You can do this with like loads of events. I've just picked out some kind of like interesting ones that I found. Here's another one. I've highlighted a region in the bottom panel there where the large-scale Poynting flux that SWARM is measuring is actually negative. And that means the Poynting flux is going up, and that means that's, in theory, that's neutral wind dynamo kind of like actually driving the ionosphere and sending energy upwards to magnetosphere instead of the typical magnetospheric driving. But then the small scale, the red line in the bottom one, is actually pointing downwards. So that's typical magnetospheric driving, and that makes sense for small scales because you wouldn't really imagine small thermospheric, stuff propagating up into the magnetosphere. It's usually the way around. So that kind of makes sense. But then if you look right there, like in between those two is the black line, which is the SuperDARM Ampere Poynting flux. And that's flat. That's completely close to zero. But then if you also took that red line, you took that blue line, you just sum them together to get the total Poynting flux, you would see nothing right? Those two things would just cancel out. So the point of me showing this is actually if you start thinking in terms of like these scale sizes, even if you don't know what those are and where to set your boundaries, you can just start arbitrarily setting those boundaries, which is what I did here with just making it look like supernon. And you can actually kind of like start to pull out these kind of like interesting things going on, like this potential upward pointing flux going on here. And then I want to finish on some very new data. This is more of a plug than anything, with the high time resolution supernon data, which I've talked about a few times of the week. If you haven't seen it, please come talk to me about it, where we basically now can operate the supernon Canada radars at a 3.5 second resolution instead of a 1 minute resolution. And on the left here is me working out the joule heating. Well, it's not quite the joule heating because I don't know the conductivity, but the heating rate on the old data and then the heating rate on the right with the new high time resolution data. And then I plotted that again on the bottom. That's just the heating rate and then the cumulative time integrated heating rate. And yeah, you can see that there's all this variability that we used to miss with the old kind of low time resolution data that we're now getting. And then overall, we end up with more heating when you integrate with time. So we're kind of getting to the point with the ground-based situation, at least, we can start to enter this realm of satellite, temporal resolution, and that kind of like lets us see more complicated data and then just makes kind of like this whole situation more complicated. So I guess the takeaway from this is what I would like to discuss is how do we really think about these scales? Because everything's pretty much always embedded, the small stuff is embedded with the mesoscale stuff, is embedded with the large scale stuff, but there is physics there. And if you just look at the data without doing anything to it, and try to say, oh, that's the Dungy cycle, or that's a gravity wave, or whatever, then it's actually really hard to do that, So that's the kind of thing I'd like to discuss. So thanks for listening.
Thank you so much. Any question? Yeah.
Very interesting talk. You can separate now spatial scales from temporal scales, or from whatever smaller scales, or can you say something about the importance? Is it more spatial? When you take a satellite, you can't distinguish like D2 or
right.
What we've done with models and creating models out of that. It's just variability, but can you say something about that?
Yeah, well, that's partly why I'm very excited about this, just because we have gone to a much higher temporal resolution now. And the good thing about supernon that it has going for it, it's got a lot of good things going for it, but that's me biased, but is that it has this fixed, field of view that is quite large. So it's fixed in space, so we can see the temporal variability. But the major weakness before was we couldn't see a lot of the temporal variability. And then a lot of the assumptions that we used to make about how quickly the ionosphere is changing now don't really hold so well when we can see it changing so much. So I think me being biased again, I think the ground-based is very important for that. And GDC would be very important for that as well. But I don't want to jinx it further than it's already been jinxed.
Great. Thank you so much. And our next speaker is Rijan Gitani.
Hello, good afternoon, everybody. Thank you for attending this late Friday session. I'm Rajan. I'm a postdoc at the University of Alaska Fairbanks. So today I'm going to present my talk on investigations on the role of local electrodynamics on high latitude F region neutral winds. So I use Fabry-Perot data collected by, so we call this deployment of Fabry-Perot as scanning Doppler imagers. The image shown here shows the typical exposure of Fabry-Perot called SDI, scanning Doppler imager. And so the neutral winds are derived from the Doppler shift of 630 nanometer atomic oxygen, and similarly the Doppler width gives the neutral temperature. So the difference of these instruments with typical narrow field FEIs is that these can look at the whole field of view at a time, so that you can divide the whole field of view into a smaller number of zones and get the line of sight wind and temperature corresponding to each of the zones. And the whole field of view is typically divided into 115 zones. So we can number the zones, like the zenith zone being zone 0. And so typically we do is zone 1, 2, 3 in the first circle, and 6, and so on. So the maximum, the zone with maximum number, just the number lies on the zenith, like near the zenith. So this is an example of the data that we get from these instruments. So this is here, this is showing the line of sight wind oscillations from Poker Flat, Alaska and Toolik Lake, Alaska. So these are, I don't know, it is very hard to see. These are the different wiggles or oscillations corresponding to that 115 zones that I mentioned earlier. So the bottom one corresponds to the zenith zone, and the one, if you go to that, they are stacked such that the topmost one corresponds to the outermost zone. And the nature of these oscillations show that they are of geophysical origin. So I mean by that, so if you go from zenith to the horizon, the oscillation amplitude increases, as you can see, and that is as expected. And also the oscillation amplitude is higher during the elevated geomagnetic activity. And so the color here shows they are color coded according to the azimuth. So here is another example of the data that we can acquire from these instruments. So this is a wind dial plot. You can think of this plot as if you are viewing down from above the North Pole. So toward the top of the plot is sunward direction, and toward the bottom is the magnetic midnight. And the time over the night advances anti-clockwise along the dial. So the arrows shown here are derived vector winds, and the color, the green hues represent 630 nanometer emission brightness, and blue through red color represent the Doppler temperature. So sorry, and in some cases, what we have seen is, so there is a large scale wind phenomena known as cross-polar jet that transports the wind from day side all the way to the night side across the polar cap and dumps it to the lower latitudes, lower than latitude of Alaska. But in some of the cases, what we have seen is those winds stall over Poker Flat, Alaska. So that kind of mesoscale behavior is normally unexpected. So by mesoscale, I mean the wind stop in a meridional distance of about 100 to 200 kilometers. So to understand those kind of mesoscale behavior, we dive into, we looked at data from 2010 to 20 and used different data sets, these STIs, Omni, and magnetometer data, and Pfizer data. And so if there is, to look if there is some correlation between these drivers, maybe local plasma behaviors and the neutral wind, and also we looked at other drivers, but the maximum correlation we see is between neutral winds. The top box here corresponds to neutral measurements, so temperature, zonal wind, meridional wind, and vertical wind. And the maximum correlation we see is between neutral parameters and magnetometer XYZ components, S component, and magnetic local time. So this is the reason we are interested in with maximum correlation. And so this is for the whole data and all time during the night. But if we look at just for active conditions, here in the next heat map here on the left, I chose only the conditions with S more than 100 nanotesla. Now we can see the correlation between neutral parameters and the and magnetic XYZ as MLT all goes to, so it goes all the way up to 55%, and so. This is data from 2012 from Alaska, the left two panels. STI measurements. Here I'm comparing the statistical result with Kiruna data because they are in the comparable latitude. So these two set show the similar pattern, and there is a noticeable change in wind direction around midnight. So, and also the reason that I looked at in the previous heat map only in the pre-midnight sector is that here we see different correlations between wind and MLT at different time sectors. So the maximum correlation, as you can see, is here during the pre-midnight sector. So here I would present some case studies that shows the variation of neutral wind corresponding to ionospheric variations, and also here is the precipitation data. So in this plot on the top you can see the onset of substorm around 10 UT. So the vertical dashed line here shows the local midnight. And so if you look at the precipitation, so unfortunately we don't have, looks like we don't have data here, but this shows that there is precipitation only in the near about the northern horizon only. So what we see is neutral wind direction change around 80 UT, but neutral temperature enhancement during the recovery phase of the substorm only, so only later on. So the response of neutral temperature, it is lagged behind, but wind shows kind of instant response with the geomagnetic activity. And these bottom three panels are ion velocity, temperature, and density. All the velocity, temperature, and density all gets enhanced after the substorm. And this is another day. Again, this vertical, dashed vertical line shows the local midnight. And so again, during the active time, so here both winds and temperature, they are more variable. And also ion density, ion velocity, temperature, and density all get enhanced after the so during the elevated geomagnetic activity. So on this night, there is precipitation throughout the field of view. So this is the bottom panel here. And so this is another day from 2016, January 31st. So again, here enhanced geomagnetic activity after 8 UT, and followed by strong precipitation on the bottom panel here, almost through the whole field of view. So if we look at the winds, both zonal and meridional winds change direction after the onset of geomagnetic activity here around 8 UT. So, but the zonal wind direction get reversed after about 2-3 hours here. So, but if you look at the neutral temperature, there is no significant change after the onset of geomagnetic activity for about 6 hours or so. And if we look at the ion parameters, all ion velocity, temperature, and density increased following the geomagnetic activity. So in summary, so large-scale neutral wind behavior changes most strongly with magnetic local time, suggesting that time of the day plays a big role. And the So comparing between neutral winds and temperature, neutral wind responds to geomagnetic activity, but the temperature and geomagnetic activity, the relation between them is more complex. So studying the differences between these events, like these case studies presented here, can help understand processes with which the ions and neutrals couple in high latitude pre or post midnight sectors. So thank you, and I am open to any suggestions that you may have. So this is a work in progress. So if I need to look at more possible drivers or things like that, if you have any suggestions, please, I welcome those suggestions. And if you have any questions, thank you.
Okay, great. Thank you so much, Rajan. Just for the sake of time, let's just follow on for this next presenter, please. Oh, you go? Okay, that was sure.
I can ask a question while you are, he has a microphone. So I want to know how you calculated the substorm onset time.
So I just looked at the magnetometer fluctuation. So and it is not the calculation. It was by like just a visual inspection. Yeah.
The reason I was asking is because if you look at the geogram in the second event, it's clear that it's a little bit earlier than the line that you have there, but we'll talk after.
Okay, thank you.
Okay, so I'm going to talk about extreme auroral electrojet during this last year's famous Mother's Day storm. So we care about auroral electrojet because it can cause large dB/dt at high latitude, which can drive GIC. I actually just presented this talk in GIC session, so sorry about the repetition. But on the other hand, extreme electrojet highlights strong Poynting flux, as well as energy dissipation, joule heating in the upper atmosphere, so that's going to affect the ionosphere and also thermosphere. And the past Mother's Day storm contains several extreme auroral electrojets, as shown here. So the top panel is SMR index, and the second panel is SMU and SML index. These two yellow shaded region highlights two intervals I'm going to talk about. The first one is interesting because if you look at here, the electrojet changed from westward, which indicates by the SML index, to eastward within a few minutes. And that magnitude of change is like 4,000 nanotesla, something like that. And the second interval is interesting because we have two SML peak or dips. These two dips occur at very close in time, like half an hour apart, have similar magnitude, similar duration, similar shape. So what's the cause of that? Are these two a reoccurrence of two substorms? By the way, for very large SML index, SML dips, people call them as super substorms. So there's a threshold about 2,500. So one, I guess, application of this study is like, are super substorms substorms? So I'm going to start with these two, the second interval, because that's one I studied. The first one is studied by Shinotani. He unfortunately cannot be here, so I'm going to briefly review his results at the end. So as said, for the second interval, we have two dips, and I'm interested in knowing whether they are two substorms. Our approach is fairly simple. We are just looking at the morphology of these two dips. So the first event, let's start with supermag. What we are looking at is polar plot of ground magnetic perturbation. These green vectors represent perturbation, and they have been rotated by 90 degrees to represent the equivalent ionospheric current. So this is the initial condition. And then at the onset, what we see is the enhance of magnetic perturbation at a localized latitude range as well as longitude range in the pre-midnight. But with time, this area of enhancement expand in latitude as well as in longitude. And and the last slide show where they start to recover. So this event is characterized by a local activation of ground perturbation that's followed by poleward and azimuthal expansion. And that's consistent with the classic feature of substorm. We also check other data set to see whether we see similar trend. On the left, we have N-peer. So different colors represent different satellites because there are 11 satellites along one orbital plane, but the colors are not important here. What we care is about the magnitude of these vectors. So this is the original condition where you see the classic two-cell current pattern, but when at the event onset, what we see different compared with the background is this suddenly appeared strong magnetic shear in the pre-midnight sector. And with time, this strong magnetic shear expand eastward. The strong shear indicates indicate field line currents, but the localized nature of the shear indicates the field line currents. And it started localized, but then expanded in local time. For aurora, we see very similar feature. This is aurora measurement at Athabasca from T-Rex array. Normally, this is an imager located around equator edge of aurora oval or subaurora latitude. But the event is, geomagnetic activity is so strong that oval actually originally, onset location happened equatorward of this station. But nevertheless, we see the aurora emissions start peeking into the field of view, expanding, and eventually engulfing the entire field of view. So again, a localized activation followed by expansion. So now let's look at the SML dip immediately following that one. And we are looking at the methodology. This slide is about supermag measurements. This is original condition, and this is during that SML dip. So what we see here is that magnetic perturbation happens at all local time. So it's not just a nice eye phenomenon, but global. In fact, we select stations at a different local time to see their onset. So we have 12 at noon, 3, so that's post-midnight, 1 around midnight, 22 pre-midnight. And this is about 15 minutes interval. And if you start to trace where the perturbation starts, they basically start at the same time, maybe within one uncertainty of 1 or 2 minutes. So that means the perturbation started simultaneously across the entire globe at all local time. And that is different from substorm because substorms usually start localized and then expand in local time. We can take a look at N-peer, similar to before. So this is original condition. This is, I believe, during the peak of the event. So what's interesting here is we don't see too much magnetic shear in the midnight, but what we see, in the midnight sector, what we mostly see is the strong magnetic shear in the dawn and the dusk that's consistent with a two-cell convection. So this doesn't seem to be associated with additional current wedge like substorm, but more like enhancement of pre-existing region 1 and region 2 current. For aurora, similar thing, we do not see expanding aurora feature, but instead we see a brightening of diffuse aurora over the entire sky. And aurora were diffused, yeah. So if we compare these two events, so are these two enhancement substorms? The first one is, but the second is not. So therefore, when people start to call them a super substorm, we should be extra careful because they are not substorms. So if the second dip is not a substorm, what drives the enhancement? So we can take a look at Omini, and what we find is that the second event, which is the dashed line here, coincide with the solar wind dynamic pressure. So it seems like solar wind pressure compress the mainosphere, enhance the general convection, and therefore lead to the global enhanced magnetic field. So even though those two dips appear more like twins in super mag indices, their driver can be completely different. And now let's move on to the first interval studied by Shinotani. So this event is really striking because if you look at, this is a magnetic field measurement from one station. The red is the north component. So this north component changed by 4,300 nanotesla within 10 minutes. So what is driving this? So now the figure on the right shows the polar plot. So this is the original condition. Here you see this strong westward electric jet, and within 10 minutes, it flipped eastward. And that stays at magnitude. So this event, different from previously, actually is a localized event. Well, not that localized, but still localized to the day side. So this is a day side phenomenon. Normally we think perturbation, especially at high latitude, is strong on the night side, but here is day side. So what is causing this day side, extra large day side perturbation? We can take a look at the solar wind or IMF condition. So this is BX, BY, BZ. So this event actually is characterized by this extraordinarily large BY flip. IMF BY changed actually by more than 120 nanoTesla. So the extreme driver or extreme variation of IMF drove this extreme variation on the day side. So this is actually my last slide. So what we're trying to highlight is we have extreme aurora events happening in the previous storms, and these can have very diverse drivers. It can be IMF, can be solar wind dynamic pressure, can be magnetotail. And yeah, the name of super substorm is an oversimplification of their nature, and we should devote more efforts to understand what are the possible drivers and what can lead to the onset of these extreme events. Okay.
Okay, great. Thank you so much, Ying. Is there any question?
Can the supermag local time indices help differentiate between what is a real substorm and these other type of events?
Yes, if you look at the MLT distribution, there are differences between these two, or all three. So one is on the day side, the other two is more on the night side. But I still want to say even that one is a little limited because if we look at this event, so if I did not show here, but if you look at the SML index, the strong SML index is still limited on the night side half, mostly because if you look at the day side, I mean, the current is north-south, so the associated perturbation is east-west. So SML is the north-south component, right? It doesn't capture east-west. So I would say it's a good index, it's good for a quick event search, but for the most comprehensive information, we should look at this kind of polar plot to get the 2D east-west, north-south magnetic perturbation.
Thanks.
Great, thank you. All right. Let's welcome Catherine Davidson.
Okay, hi everyone, I'm Kat Davidson. I am a postdoc at Boston University, but this is some work that I did with Gong during my graduate studies, and that is data model comparisons of high latitude ionosphere-thermosphere coupling during the St. Patrick's Day storm in 2013. So quick background and motivation. Neutral winds are important, especially in the high latitude. High latitude neutral winds during storms can modify the Joule heating rate and also redistribute the mass in forms of TADs and TIDs. However, there's no clear consensus really on what forces dominate the neutral wind behavior, especially during the storm time. So things such as ion drag versus Coriolis force versus advection forces. And additionally, depending on what model input you use to simulate the neutral winds, the winds and the forces can vary greatly. And so these are the two objectives that we had for this study, which is determine the dominant forces of the neutral wind response, and also determine how the high latitude input varies thermospheric forcing and the corresponding neutral wind response. So in order to do that, we take TIGCM and we do 4 model runs. The first set of runs is to compare the difference between empirical driving and realistic driving. So we use Weimer and an analytical model to drive for our high latitude input into the TIGCM model. And then for the realistic drivers, we use AMY, which is a data assimilation model. So it uses real data to for the high latitude input. And then we wanted to also test the effects of the auroral precipitation specifically on the neutral wind output. So we manually change the auroral energy flux from AMI, decreased and increase, and assess the output. So for each of these runs, we compare the simulated neutral winds to the neutral wind observed by the Poker Flat SDI. And then we also calculate the individual thermospheric forcing terms for each run to determine the dominant forces. So for our first run here, this is the empirical versus realistic neutral winds. These figures in the top 3 panels are kilograms, so latitude or longitudinal slices of the neutral winds, and then our latitude is on the y-axis here. In the top panel, we have the observed winds, zonal or east-west, and then meridional or north-south direction. In the middle panel, we have the winds driven by the empirical model or Weimer, and then the third panel is the winds driven by the AMI or realistic driver, and these are taken at the same longitudinal slice as our observations. And then the bottom panel is our errors, and we chose to do a root mean square error for the magnitude, and then also a correlation coefficient between the modeled winds and the observed winds, so that we can observe the spatial error as well. And what we found is that the realistic driver here very clearly better simulates the pattern of the observed neutral wind structure. And we can see that in the error. The dashed curves are the realistic drivers, and then the solid curves are the empirical drivers for the error. And so we had a higher magnitude error in the realistic driver, and you can see that from this, you can see that, okay, from this higher magnitude here and here as compared to the observations. But the spatial error is a lot better in the realistic driver, so we're capturing those structures a lot better. In the zonal direction, the empirical driver greatly overestimated the meridional wind speed, but the structure were actually pretty similar between the 2 runs. So because the realistic forcing AMI driver better captured the neutral wind structure, we're just going to look at the forces from that run. And so what we have here is the forces on the same longitudinal slice as our observations, and we have all of the forces here on the left, and then the total forcing on the bottom, which is just the cumulative sum of all the forces. And we determine the dominant force by basically just visually identifying what patterns are most dominant in the total forcing from the other forces. So, for example, the total forcing in the zonal direction here is very clearly dominated by the ion drag, and it also has contributions from horizontal advection as well. And in the meridional direction, we have a pressure gradient as a dominant meridional driver, and you can see it has this periodic northward and southward driving, and this is a signature of something like a TAD. And so moving on to the auroral energy flux test results, we have the same type of figure here. So our observations are in the top. The decreased energy flux is in the middle, and then the last panel is the increased energy flux. And we see that the decreased flux maintains the same structure, but just decreases the zonal wind speed. So we have a very similar correlation or spatial error, but we have a lower magnitude error. However, the increased flux actually changes the structure and increases the zonal wind speed, so our spatial error is much higher, as well as our magnitude error. And there's a less significant change in the meridional direction, and this is because most of the forcing associated with auroral precipitation is normally east-west aligned, so we don't see much change there. So again, we saw a more significant change in the increased energy flux, so I'm just going to show you the forcing analysis from that run. And you can see here that the ion drag, or zonal ion drag and horizontal advection greatly increased, so much so to the point that the total forcing is completely dominated by the ion drag, and we no longer have that force balance between other forces like pressure gradient and Coriolis forces in order to make the winds more similar to our observed winds. So even though ion drag is a dominant force, force balancing is still really important here. And in the meridional direction, the pressure gradient, ion drag, and horizontal advection all increased, but the final forcing pattern is still pretty similar to what it was before. So that's again why we don't see much change in the meridional direction. So just to go back to my key questions from the beginning, we wanted to determine the dominant forces of the neutral wind response, and we saw that ion drag and horizontal advection were dominant in the zonal direction, and pressure gradient was dominant in the meridional direction. And in terms of how the high latitude input varies thermospheric forcing and the corresponding neutral wind response, we saw that Amy better captured the observed neutral wind patterns than Weimer, especially in the zonal direction. And this is again because ion drag is a dominant force. So when you use a more realistic convection pattern, you're going to get more realistic ion drag and then winds that more closely resemble your observed winds. And we also saw that the convection heavily controlled the neutral wind structures. Again, this is because ion drag is a dominant force. But the auroral precipitation more influenced the neutral wind magnitudes, but the structure kind of remained similar, especially in the decreased flux case. So I went through this really quickly, but I do have a paper on this with more results and more details. So if you have any questions, please refer to that. And thank you.
Thank you, Catherine. Any question? Okay, great. From our next speaker, we'll have Shanshan Bao from the Rice University.
Hi everyone, I'm Shanshan Bao from Rice. I'm also a member of the CGS team. Today I'm going to talk about my recent study of the investigation of newly defined ionospheric superdepletion structure. I will use the September 2017 storm as an example. People may be quite familiar with conventional equatorial plasma bubbles. Basically, they're a cluster of small-scale, low-density bubble that generated from the post-sunset magnetic equator, and a previous study show it is triggered by the Rayleigh-Taylor instability. However, recently there's a newly defined ionospheric depletion structure called the bubble-like ionospheric superdepletion structure, BLEAS. And it is distinguished from the conventional EPBs for three key features. First, it is manifest as a single depletion channel that at post-sunset with larger longitudinal widths than EPBs. And it can reach to a much higher latitude, for example, to the subaurora region around 40 to 50 magnetic latitude. Also, its depletion path has a prominent westward tilting, and its mechanism is still not clear. To really understand the electrodynamic coupling each step out of the way of how this ionospheric structure formed, we really need a whole geospace model. So here we use the MAGE 1.0 version, which has a global MHD code driven by the solar wind, and it is coupled with an ionospheric electric potential solver. It will provide electric potential at high latitude in TiGCM, the upper atmosphere model. So it also coupled with the Rice convection model, the ring current model, and both RCM and MHD will provide electron precipitation to TiGCM, and TiGCM is actively tracking the electron, ion, and neutral species, provide us with conductance feedback to the electric potential solver, and produce the TEC at each time step. So here is our model data comparison. So here you can see the development of BLEAS has three stages. First, it initiated from the magnetic equator at the post-sunset region. Then it expand with an obvious westward tilting angle and toward mid-latitude, and eventually it merged into the mid-latitude density trough. Our simulation successfully reproduced those features. So our next step is to investigate what is a major contributor to the depletion. So we use O+ as a proxy of the electron population because it's a dominant ion species in the F region. And we investigate the rate of change of O+. So it is mainly contributed by, first, the M bipolar diffusion, the E cross B transport, neutral wind transport, and production and loss from chemical reactions. And you can see in this latitude and longitude map that this E cross B transport is a major contributor to the depletion. So as you know, that the total E cross B transport can be divided into the horizontal E cross B and the vertical E cross B components. So we investigate their contribution separately. So the top left panel shows the vertical E cross B drift velocity, and here is the its rate of change in O+ contributed by it. And on the right panel, although you can see the meridional E cross, the horizontal E cross B drift velocity is quite large, but its contribution to the depletion is quite limited. And on the right, I'm showing how this TEC depletion initiated. It's right after the sunset, and you can see there's a upward E cross B drift causing depletion in the altitudinal direction. So our next question is, what is the source of this low to mid latitude E field? So there are two possible contributors or sources for mid to low latitude electric field during storm time. First is the penetration electric field. The other is neutral wind dynamo. So we did a numerical experiment in TiGCM. So here, the top panel, I'm showing the total electric potential with the black vector, which is a neutral wind velocity. And I turn off the neutral wind and evaluate the potential instantly. And you can see the potential pattern remain almost the same, and the potential difference is quite trivial. So we conclude that the neutral wind dynamo effect is quite trivial, and the penetration electric field is a primary contributor to mid to low latitude electric field enhancement. So here I'm showing the O+ density and the rate of change due to E cross B transport. And you can see there's a moment of a sudden enhancement of this O+ depletion. And if we mark those moments onto the solar wind profile, and if you look at the this panel, the orange curve, which represents the BZ components of the solar wind, you will see those sudden enhancement time time points correspond to the sudden drop in BZ. And in the magnetosphere, you can see that due to the sudden BZ drop, there's a prominent enhancement in the region 1 current. However, the region 2 current is not strong enough to show the region 1 current effect. So basically, that caused a prominent undershooting condition, and in the ionosphere-thermosphere, it is resulting prompt penetration electric field. So that effectively accelerates the bliss development. So basically, here is the electrodynamic pathway in the bliss development. Next, we investigate the cause of the initiation. So there are two possible causes of the bliss initiation at post-onset equatorial region. First is a penetration electric field we just talked about. The other is pre-reversal enhancement, which is E cross B vertical drift that uplifts the low-density region at post-sunset. So on the left panel, we're looking at quiet time. This is O plus density profile. You can also, we're looking at the vertical drift, E cross B drift velocity. And obviously, you can see this PRE show up in the upward plasma drift. However, if you probe along 5 degree and 20 degree respectively, you can see that there's a depletion in the O plus at 5 degree. However, it cannot propagate to higher latitude and 20 degree. So on the right, it is during storm time that it has a combined effect of PRE and the penetration electric field, which you can see this upward E cross B uplifting can be picked up by the penetration electric field and expand all the way westward and poleward to higher latitude. So we conclude that the initiation of bliss has a combined effect of pre-reversal enhancement, and it provides a preferable condition for its initiation. And the penetration electric field is a necessary condition for its further development. That also explains that why bliss manifests as a wider depletion channel originating from the post-onset magnetic equator. Here is a summary. First, we successfully reproduces bliss super depletion structure by MAGE, and also we conclude that bliss is initiated by the concurrence of penetration electric field and the pre-reversal enhancement. And basically its development is driven by the western poleward through E cross B transport. Also, the sudden drops in the southward solar wind BZ induce strong prompt penetration electric field that facilitate the development of bliss. So for more details about this study, please check my recent publication on GRL. And also, I want to emphasize to study such mesoscale structure, especially during storm time, we really need a whole geospace model that couple the entire system. So just as an advertisement that the model I have been using for this study is public available, and it is, you can submit run on CCMC to first try the model out, and it will really help you out on the storm time dynamics study. Also, we have this open source release for a new version of the model. Yeah. Basically, that's it. Thank you.
Thank you. The time is limited, so we go on to the next speaker, Chen Wu.
let's follow up on the MAGE and the penetrating electric field. And so, as the previous speakers mentioned, that the equatorial ionosphere can feel the direct penetrating electric field, and also slow, disturbed electric field. And there's a great interest. Understand, that how the penetrating electric field without the disturbed electric field, how it looks like. And we used the MAGE model, did a simulation on one of the cases. And additionally, we also had icon observations to help validate some of the simulation results. So the event I'm looking at is July 7th and 8th, and 2022. It's not a major storm, and we had 2 cases of the IMF-BZ, which is on the third panel. Hmm? All right, 2 cases of sudden southward turning of the IMF-BZ, and that provide a case of in first case, which start with a quiet condition, and second case with have a disturbed conditions, and you apply the penetrating electric field into it. And you can see that in the KP index where this happened, and the first one started with pretty quiet condition, and with a high KP level with the second one. So in the first case, look at the polar cap, that the potentials, from 50 kV to 100, something like that, and with a southward turning. And we extend this kind of potential map all the way to the equator. You can see that how the equatorial region feels this kind of potential, that the down dusk potential is generating eastward penetrating electric field on the day side, and the westward penetrating on the night side. And it's pretty uniform and apply across all the different local times over there. And if you look at the vertical ion drift at the magnetic equator, you can see that on the night side that the doubles the downward drift, and that's a result of a penetrating electric field. And it's a pretty clean penetrating electric field applied to this. And we look at the icon neutral winds and vertical ion drift. Unfortunately, in this case, the timing is applied here, highlighted here. And the vertical ion drift during that time period was not in the ideal location, so the data was not very clear to us. But overall, that the neutral winds, the zonal winds at the beginning, from below to up above, and you can see that at the beginning the zonal winds are pretty smooth, not much variations there, and after the thing comes along, you can see the nighttime that you can see the zonal winds are starting disturbed. The triangles indicating the local midnight time period. And in the next case, we can highlight it one more time and see how the IMF conditions look like, and where the IMF-BZ take a break and went to northward conditions, and somehow, and sort of turn off the PCP, and but the storm's still going on, but and make a sharp southward turning over there, and so you can see that at the beginning of this, and you can see pretty low PCP, and then later on, once it turns southward again, and apply a high voltage onto it again. So, but this time you look at the potential all the way to the equator. On the day side, you can still see the pretty clean eastward electric field, but on the night side, you see this kind of potential bulge there, and before midnight, and so it is sort of a non-uniform anymore right now. So then you look at the vertical ion drift. It's not uniform towards downward drift. There's a region that you see upward drift. And when the penetrating electric field applied to it, and that's applied to the ion drift, go to downward. So it reduces the disturbed electric field. This is probably due to, we saw this due to the zonal wind dynamo causing this. And fortunately, we have icon to look at the zonal winds, and with the icon with the MAGE simulations, and on the left, the icon neutral winds, zonal winds, you can see the disturbances on the night side, and also you see the increase of the vertical ion drift on the right side over there. And for more detailed comparison, we plot this for the first case and second case. You can see in the second case that the dots are the observations, and the lines are the simulations, and the simulation roughly reproduce what the observation shows, but they are not as big as the icon observations shows mighty winds, the zonal wind observations there. And the vertical ion drift is a little bit later than the observation shows, and observations certainly because you have a larger winds and generate a much bigger vertical ion drift, upward ion drift. So in summary, we get to this event to look at the case that the penetrating electric field coming from in quiet conditions versus more disturbed conditions with a disturbed electric field. And the quiet condition, of course, give you a more uniform apply to the daytime and nighttime. And disturbed conditions, you introduce a structure on the night side with a penetrating electric field and disturbed electric field mixed. And the penetrating electric field tend to reduce the disturbed electric field on the night side. And MAGE simulation pretty much capture that, but in the magnitude size, there's still some improvement can be made on that. So I stop here. Questions?
Any questions?
All right. Must be late on Friday.
Very much.
The paper is already published. You can take a look at the paper too.
Oh. Yeah, thank you very much. Yeah.
Our next speaker is Kalle Landau.
Okay, thank you.
Okay, so I will also show some model data comparisons of penetration electric fields at low latitudes. But we use a different approach. We have developed a new method to do MI coupling. So I'll spend the first part of this talk describing that approach. So the conventional approach is shown here. Let's see if I can use, yes. So this is an animation of the Gamera MHD model. It is coupled to the ionosphere. It's illustrated here. The input to the ionosphere is field line currents that are derived from the curl of B in the magnetosphere, and then the output is the electric field. And that electric field is calculated by solving the current continuity equation, which looks like this, using the ionospheric Ohm's law. And this is like an electric circuit, so it's like a circuit approximation. What we do is slightly different. Instead of using this current and electric field as a primary parameter, we use the magnetic field, and we use Faraday's law. So we also have a 2D ionosphere, and when we evolve in time the radial component of the magnetic field. To do that, we need to know the electric field, and the electric field is given in the second equation here. That's the generalized Ohm's law. In this case, it is just basically the ionospheric Ohm's law solved for the electric field. In that equation, there's the surface current, Js. To replace this, we use Ampere's law, which is last equation on the slide. And that equation that involves a magnetic field just above the ionosphere and below the ionosphere. So the next step now is to define what these are. Once we have that, we basically have an equation for the magnetic field, the evolution of the magnetic field that depends on the magnetic field itself. And then the electric field can be calculated from the generalized Ohm's law. There's a QR code on some of these slides. It's supposed to be a link to a preprint of the paper where this is described. Yeah. So the magnetic field, the above and below the ionosphere. Below the ionosphere, yeah, so we decompose the magnetic field in what we call induced and imposed parts. So below the ionosphere, the magnetic field is purely induced, and it is fully defined by BR on the surface of the ionosphere, which is what we evolve in time. Above the ionosphere, B+, the magnetic field is a combination of induced and imposed. The imposed part of the magnetic field is a magnetic field that describes field line currents that are defined on high latitudes, so you can still prescribe field line currents and use this approach. It also includes more remote magnetospheric currents, and at low latitudes it satisfies two constraints. The first constraint is that the current is continuous between hemispheres. That means that current that leaves one hemisphere enters the other hemisphere on the same field line, and also that the electric field maps between hemispheres along magnetic field lines. So once we have all of this defined, we can calculate the electric field and electrodynamics globally, given some input. So here I will show an animation where the input is this conductance, this wind pattern, which is a static wind pattern from the horizontal wind model, and then we switch on this high latitude field line current pattern. And at t equals 0, this simulation starts at steady state without any high latitude field line currents, and then when we switch on the field line currents, we get this development of the electric field. The black contours, that's the electric potential, and you see that it evolves in time due to induction. The orange contours was the induction electric field. So this is now the penetration electric field at low latitudes. We can also do a steady state solution. In that case, we set Faraday's law to 0, and we solve for the induced field given the imposed field. So this is then equivalent to an electrostatic solver as used in MHD models now. Except that we include parts of the magnetic field that are not accounted for in these models. So in the past week, I have run this steady state solver using to calculate the penetration electric field for this event that was published in 2003. This top plot is from this paper by Kelly, which is Ikamarka vertical, eastward electric field. And then I run our solver using an empirical model as input for high latitude currents, an empirical model that depends on the IMF and seasons. I used EUV conductance from a paper by Art Richmond, and static auroral conductance, but it rotates as time goes, and no wind. And then I get this penetration electric field at Ikamarka, so which corresponds quite well to the observations. If we scale it and a little bit, then you see that the amplitudes, the variations match really well, or amplitudes are a bit a bit stronger, and there's a deviation towards the end of this. But I think given not optimal input, that this is a quite good agreement. This is my last slide also, so I'm happy to take questions. Thank you.
Very much. It was a great talk. Any questions?
Cool, thank you. Excellent talk. Just quick question on the first, like a few slides ago where it said penetration. Yeah, input Hall conductance, where did that come from?
It's a Hardy model for the polar region and just a model of the EUV conductance for low latitudes.
Cool, thank you.
Any questions? Okay, so thank you very much again. And then,
yeah, so thank you for this talk. I'm going to have to study your mathematical formulation to understand it better myself. But if you go back to your first slide with the math on it, when you specify this delta B minus below the ionosphere, so that's the magnetic field perturbation in the gap between the surface of the Earth and the ionosphere. Do you need another boundary condition at the surface of the Earth that depends on ground conductivity?
Ideally, yes, but we don't have that, so it's like the Earth is not there in this case. But you could add a boundary condition to make a more realistic treatment of induced
So when you say it's like the Earth is not there, wouldn't it be better to treat the Earth like a conductor?
It would, yes, it would, yeah.
discussion. And so the next speaker, thank you. Yeah, thank you for the next speaker is Kevin Pham.
All right, thank you. So I'm going to talk about MAGE simulation for the May 2024 storm. So for the MAGE version I'm using here is MAGE 1.0, which is available on CCMC. It has TiGCM 3.0 coupled to it. And because this is such a large storm, you really need MAGE 3.0 to get better vertical resolution. So we had to switch things from quarter scale height to 1/8 scale height in this case, and then we went up from pressure level 7 to pressure level 9. We also had to, because it's such a large storm, we really want to capture everything in the storm. The Gamera inner boundary, which is normally about 2 RE, we pushed that all the way into 1.3 RE, which maps to about 30 degrees, 30, 35 degrees or so in the remix electrodynamics latitude there. So for this storm, rather than using Omni, which you can see on the right there, it has a little bit of I've highlighted this region in Omni in which the solar wind, there's a transition in the solar wind, and then Omni propagates it, and then you get this huge variability in the velocity. We decided to use just a constant wind, take wind and then just do a constant propagation. It's about 30, 31 minutes or so to the Earth's bow shock from wind location. So you don't get this artifact with wind. But then at the same time, we also did it with another run in which Artemis and MMS are out in the solar wind. So using Artemis and MMS, we constructed a closer to Earth solar wind. So this is a comparison of the wind versus the Themis MMS combined solar wind. So the wind-based solar wind is in blue, and the orange is the Themis MMS combined solar wind. So you can see while in general they're pretty close to each other, there are some variations, particularly in the density. You see a lot more density variations with the Artemis and MMS. And then also in BZ, there's a very large discrepancy at one of the at around 1830 UT or so, wind is showing something like -20 nanotesla, while Artemis and MMS is seeing -50. So it's a very large difference. One bonus that we get from using Artemis and MMS is that you get a 4-second time resolution instead. Well, it's like 4 and 16 seconds. So we interpolated 4 seconds just to improve things. And that's better for shock capturing the shocks. For example, here there's a big BY flip. So you can see in blue, The blue takes a couple minutes to go from -50 to +50 in BY, while in the orange, you can see that it ramps up within a couple of seconds. And so it's a much sharper shock using the Artemis and MMS solar wind data, and so you get much better timing. So in the interest of time, I'll just quickly go through this. So GOES 16 is on the day side, and there's using the improved solar wind, you can see that we do a whole lot better than with the wind-based solar wind at GOES 16. Similarly for GOES 18, we also get a very large improvement. But if you want to take a look at the MI coupling global system parameters, for example, so for polar cap potentials at the very top, the wind base is in blue still, and the improved Artemis MMS solar winds in orange. So you can see that there's not much of a difference in terms of the polar cap potential in the northern hemisphere. You see a little bit more of a difference in the southern hemisphere, but overall it's not that different between the runs. But between north and south, you can see that for the northern hemisphere, we're reaching somewhere between 250 to 350 kilovolts. In the southern hemisphere, at some points in time, we go up to about 500 kilovolts in the simulation. So you get a lot more polar cap potential in the southern hemisphere for this May storm. And then if you take a look at the integrated field line currents, which is in the middle panel there, the northern hemisphere, the two runs appear to be really similar. In the southern hemisphere, you see a larger difference in the southern hemisphere coming from the improved MMS solar winds. So you do get a lot more currents going into the southern hemisphere than you do in the northern hemisphere. And then as far as hemispheric integrated precipitating power, they're about the same in both hemispheres, give or take some small variations, but that's mostly because the dominating source of precipitation is the diffuse precipitation. And in our model, we're mapping the diffuse precipitation equally to the two hemispheres. So when you take this and you take a look at what's happening in the ionosphere, with TiGCM 3.0, and we're extending it up to much higher pressure levels, we're able to go through the DMSP altitude, which is about 840 to 850 kilometers. So what you see on the right is 4 different passes from DMSP F18. The DMSP location is marked in blue, and then in the color panel it's marked in blue, and then the background color is the vertical slice from TiGCM. And you can see the line plots right below that. So for example, in the first pass here, DMSP sees this really large bite out in the ion density, and then TiGCM also sees a large bite out, but in terms of the simulation timing, we're seeing ours a little bit before DMSP, and if you, I don't have it shown here, but if you do a global plot of this, it's a slight difference in spatial. So DMSP, the location of our bite out is a little bit off compared to the location in F18. And then you take a look at the next panel here. It's a similar bite out. We're a bit deeper, so we're overestimating we're overestimating the heating here, and so we get a much larger bite out than what DMSP is seeing. And then similarly, again, on the third, we're seeing a deeper minimum, and you can see there's like some sort of structure, like a bubble or something in between in F18 that we don't have at all in the simulation in TiGCM. And then we do an okay job on the last flight here. So overall, we are getting this bite out, and you can see in the bite out, this is the electron density, and the bite out. The electron density is that whole column is pretty much evacuated of electrons. There's not a whole lot of electrons here. It's they've all moved upward and kind of out of the simulation domain here, or to a little bit higher latitudes. And another thing is taking a look at the total electron content, TEC before, after, and during the main phase. So before the storm is on the left here, and before the storm we do the observations on top, and then the simulators on the bottom. We do a pretty good job in terms of capturing capturing the TEC. We do see a little bit of a plume in the southern hemisphere that you don't really see in the observed. And then if you take a look at right during the main phase, or like immediately after the main phase, in the middle panel here, you can see that there's a very large TOY, or a plume coming out of coming over across southern Australia and over New Zealand. You can see that in the observed. You can see it's a red spot going across right here. We're capturing that in the model as well. And the interesting thing for this one is that the source for this TOY is not your typical SED. It's actually, you're pulling it from the EIA. So the EIA is being enhanced in the the equatorial region, you're enhancing the EIA, and then it's so big, our convection patterns are so large and low latitude that we're actually entraining all of that from the EIA to form a TOI. And then at the very late in the main phase, or not main phase, in the recovery phase, we still see something that looks like a TOI in the simulation that you don't get at all in the observed, and so we're overheating a little bit compared to what the observed shows. The other thing that we see in the simulation is that the EIA becomes really enhanced. It gets uplifted to a higher altitude and becomes really enhanced, and it sticks around for a really long time. So in this case here, we're getting close to dawn again, and you can see there is still EIAs sitting over Japan and over northern Australia, and you also see that in the observed as well. So we are seeing that the EIA is living for a really long time. And then lastly, the neutral density comparison is not necessarily ionosphere, but this is higher altitudes. So if you compare, so the simulated in this case is in blue, and the observed is in orange. And you can see if we compare to GRACE follow-on, we do actually a really good job. We're right on top of what GRACE is showing. There are some small differences, but overall we're doing a really good job in comparing to GRACE. And then similarly with SWARM A, B, and C, but you can see that the SWARM measurements are a little bit more average than what we have in the simulation. So there's not as much variability in the observed. All right, so in summary, using the closer to Earth solar wind gives you a very big improvement over L1 observations. The ionosphere is really expanded, particularly in the southern hemisphere. There's a lot more heating happening in the southern hemisphere. And DMSP sees these columns where the F2 region is above DMSP, and we're capturing that pretty well in the simulation. We also see a storm-enhanced EIA, which becomes the source of the TOI, and then we also see the EIA persist throughout the night just because it's so enhanced. All right, thank you.
Thank you very much. Any questions? No questions. Everything was so clear. Thank you very much, Kevin. The next speaker is Samuel Walton.
Okay, thank you very much. Today I'm going to be presenting an example of an event in the inner radiation belt, which is driven, we think is driven by electric fields, which could potentially be resulting in significant electron precipitation in the low latitude, at low latitudes. So an example of a previous version of one of these events is observed here by low altitude spacecraft called Demeter. You can see the latitude, longitude map of the Earth here. And what this color represents, this is an event from a paper published in 2019. And what you can see here is an example of 200 keV electrons precipitating in the space of a few days, quite high fluxes into the atmosphere, and believed in the paper, the reference there, it's Selesnik et al. 2019, but believed to be ultimately driven by geomagnetic activity, and then the direct driver of this precipitation being large-scale electric fields close to Earth at very low L shell, so very close to Earth. So an example of one of these, an example sort of from further up from observed by Van Allen probes here of these events from September 2017. Shown here, so the sort of the quiet time before this event is shown here, and what this is. Apologies for the small labels, but on the x-axis here is time, and this is about 1 hour of time, and on the y-axis is electron energy from about 30 keV up to about 800 keV, and the color there is the electron flux. And so what you can see here is the spacecraft in the inner radiation belt, and then dropping below the inner radiation belt, which is why the fluxes drop below the noise floor, and then back up into the inner radiation belt around the equator. And then the plot below that is the same layout, but in the tens of keV here, we can see, so this is about 9 hours later, so one Van Allen probe orbit. You can see there that lots of, or a high flux of 10, I think it was like 10 to 70 keV electrons in what should be the drift loss cone. So they should be precipitating and hitting Earth at these low latitudes near the equator. So the question we're asking is essentially what, from a radiation belt perspective, what is the origin of these particles? But more relevant to this session, like, can we quantify this precipitation? And can we show that it's a result of electric fields? And can we quantify the precipitation that hits the atmosphere? So we do this by taking these observations, shown the plot you've already seen in the bottom right-hand corner, as an initial condition during quiet time, and setting up a bunch of particles in the same region around the Earth. These aren't lines, they're lots of dots. I should have made them smaller. But setting up some particles in the same region and giving each one of these particles an assigned amount of flux, to put it simply, from the observations for that simulation to then carry that value through the simulation. And the top right plot here is just GSM X and Y, so you're looking sort of down on the Earth at the North Pole, and it's an example for the 70 keV electrons, but the simulation contained all these energies. And the basic setup is like that, and then we just push the particles each time step by using the gradient drift and the magnetic field from the IGRF model. And then we also add the Feyer and Schlius ionospheric electric field model onto that simulation. So I don't know too much about this. I'm a radiation belt person. So this is apparently the best one to use, or one of the best one to use. I'm happy to take inputs on all of this to try and improve the model, but we use this, which is a MLT dependent. So this top panel here is the drift velocity that the model applies, the electric field applies to each particle through the 3 days that I'm simulating, and the x-axis is the MLT, the local time variation of that, and then the color on there is just the time, and then here is the MLT on the y-axis again, and then the time on the x-axis, the color being the drift velocity. So during these 3 days, you sort of get 3 kicks of the electrons, the 3 kicks of the electrons in either direction, and the bottom panel here is just AE over time, just to show that there's 3 bursts of activity. And so, just the first thing, to validate our simulation, the top panel is what you've already seen. It's during the event happening, and then the simulation is shown there for 70 keV at a similar time. So just so the observation is from the night side, equator, low L shells, so L of 1.15 to about 1.3, and we can see here on the night side those 70 keV particles are much closer to the Earth than the initial simulation. I have more plots to validate this, but just to show it on here. And then, oh, that's supposed to be a video. Never mind. You'll have to trust me that these move around in a circle. But when we run through the simulation, this on the bottom right here, we have the electron flux that hits the atmosphere over time. So this is the 3 days from September 6th through September 9th. And these spikes here are sort of the different colors are for the different energies as labeled there. So the blue is the 0 to 50 keV, the orange is the 50 to 150 keV. And you can see over time here, so after about a day of the quiet time, we get multiple bursts of high flux. So the flux unit, it would be about 10 to the 5 of these flux units, centimeters squared per second per radian per keV, hitting the atmosphere. So by all measures that I recognize, that's a significant amount of precipitation at low latitude. And before we go on to where it hit the atmosphere exactly, we just from a radial transport point of view, these electric fields we think are moving the electrons inward by about fractions of an L shell, fractions of an Earth radii, which translates into over 1,000 kilometers. So these here are the particles in the simulation that ended up precipitating and hitting Earth's atmosphere. And these have come in from the highest L of 1.25 all the way to hitting the atmosphere. And again, most of those traveling about 1,000 or so kilometers and precipitating. So a significant loss from the inner radiation belt, which is important for radiation belt physics, and then what I understand to be a significant precipitation hitting the atmosphere as well. And we only ran equatorial particles, so it's no surprise that these particles hit on the magnetic equator, but they do hit sort of within, where are we now? 120 to 180 degrees east, so west of the South Atlantic anomaly, reasonably west of the South Atlantic anomaly. So that kind of makes sense. These dots here are colored by energy, and yeah, it happens, as we've seen shown in the time plot before, it happens in a few little bursts there. And so that's where we are right now. The summary is up there, and the sort of next few steps are, we want to verify, is this really real? So that's the simulation telling us. Simulations have all sorts of assumptions and errors. So is it real? Can we find some ground-based data at those latitudes that could verify this, or does anyone know that this happens from a sort of looking up point of view from the atmosphere, ionosphere perspective? And is the precipitation, is it significant? And do people who study the ionosphere and the atmosphere care about this amount of precipitation? And I'm very open to collaboration and input on this, because like I said, I'm very much a spacey person, and I would like to hear the perspective of someone who works on the ionosphere. So I'll leave it there. Thank you.
Thank you very much for the interesting talk. Any questions? If not, may I ask you a question? Sure. So you use the Farron series model.
Yes.
And because this is a very significant storm, are you using a disturbed version of the empirical model, or are you using a quiet time drift?
It should be the disturbed version.
Disturbed?
Yeah.
Okay.
It was a while ago, but I can confirm.
Okay, thank you. Oh, okay. Any other questions? Okay, thank you very much. So the next speaker is Dr. Prakash. I'm so sorry. What the first name? Sorry. Arumina Prakash. Yeah.
You almost got it. No worries. Hi, everybody. My name is Arunima Prakash. I'm a PhD student, actually, to be doctor eventually. I would like to thank the organizers for giving me this highlight talk. And I would like to thank my advisors, Dr. Navarro and Dr. Thayer, for guiding me and giving me insights for this talk. I'll be talking about the ETA and the impact on it during the May 2024 geomagnetic storms. And this is a preliminary results that we are showing now. So EIA is very common, and we've heard about EIA and the impact it has on geomagnetic storms quite a bit. But the impact the ETA has not been discussed as much. To give you a quick reference, ETA is the less popular brother of EIA, which is the equatorial thermosphere anomaly in the neutral density area. So basically, you have a trough at the magnetic equator, and then two crests like around 20 to 30 magnetic latitude. And there have been some studies that talk about the simulations of TIE-GCM in geomagnetic active periods, and they think that by enhancing the ETA enhances during weak geomagnetic storm times. But under stronger geomagnetic influence, they think that the crests of the ETA kind of are overshadowed by mid-latitude and high-latitude heating. So for this study, we basically looked at the GRACE follow-on data. So this is right before the storm. I have the y-axis as the magnetic latitude, and the x-axis is my relative neutral density with respect to the background density. So you can pretty clearly see, like, we have the magnetic equator here and the trough there, and then the crest kind of forms around 20, 30 degrees. And this is typical behavior that we would expect out of ETA in weak or no geomagnetic activity. But the interesting part is here, which is during the main phase of the storm, we actually see the ETA get enhanced into a super ETA. Now, there have been studies about how the EIA during this time has also enhanced and expanded to 20 to 40 mid-latitude regions. But this is the first time that we are seeing ETA observations using GRACE follow-on that show this as well, which is super interesting. And again, this is preliminary work, and we are working on getting more finalized results, but it was interesting to share. Thank you.
Thank you very much for the interesting result. Any questions?
Yeah, thanks a lot for the very interesting result. I think of the thermosphere as being a lot heavier and a lot slower than the ionosphere. So how long does it take the thermosphere to respond to changes in the EIA? Like, is there a time delay between the ETA and the EIA because the thermosphere is so much heavier?
Right, that's a very good question. I am kind of working on that result. There should be a little bit, but to give you a definite answer, I'll have to get back to you. Thank you.
Any other questions? I don't know if Kevin, did you look at the ETA in your simulation? Okay, but you have it. Okay, that would be great. Yeah,
we should talk as well.
Thank you very much. So the next speaker is Yan Mei.
Hi, I'm Yang Mei from a PhD candidate at Boulder working with Professor Xin Li, and today it's my pleasure to present this talk on behalf of Professor Xin Li. So the topic is the relativistic zebra stripes measured by Serbi Reptile 2 and their physical implications. We'd like to thank all our co-authors and also especially acknowledge Dr. Celine Lejean and Dr. Naomi Maruyama for their insightful discussions and contributions to this work. So let's start from this plot. It's showing the ionization rate of as a function of altitude by different precipitating particles. The pink area is showing the radiation belt electrons, and it is energy dependent. So this plot is showing the penetration depth of different energy precipitating electrons, and we can see that the higher energy electrons tend to penetrate to lower altitude. So this is just suggesting that high energy measurements is very important for us to understand this kind of coupling better. But in this talk, we will focus on how the electric field can modulate the radiation belt electron behaviors, and it's also revealed by high energy resolution measurements. So just a brief background of radiation belt physics. Like the particles in the radiation belt just continuously undergo the three different periodic motions, including the gyration, bounce, and drift. And in addition to the medium or high altitude orbit satellites like the Venom probes, the low Earth orbit satellites, for example, SAMPEX, POSE, CSSW, CERBI, also provide many important measurements, especially at the lower L. And just a brief review of the history and development of Reptile and Reptile 2 instruments. So the Reptile instrument, also known as the relativistic electron and proton integrated little experiment, was developed over a decade ago, and it has 6 energy channels in total for electrons and protons, and it was on board the CSSW CubeSat, which is a very successful mission. And years later, there's Reptile 2, which inherited the core design of the Reptile, but also has a new design of the guard rings, so which ensure clean measurements. And more importantly, it has 129 energy channels for electrons and protons, so that largely increased the energy resolution. And it is on board the CERBI CubeSat, which is a sun-synchronous high inclination low Earth orbit satellite. And for this kind of orbit, the location where the measurements were made is important because that determines what kind of electrons we are looking at. For example, the red here is for precipitating electrons that will precipitate within 1 bounce period, and the green is quasi-trapped electrons. They will continue to drift until they reach the SA region, and also the colored region is for trapped electrons. So the particles there will be stably trapped. And eventually, let's get to the observation. So a few days after its launch, CERBI was able to capture the radiation belt response to an intense storm on April 2023. And this figure is just showing one of the many interesting features captured during that event. So here, the electron flux is shown as a function of energy and L. And we can see that there are distinct energy band structures showing up. And if we further do the detrending process, and then shown by this panel C, we can see these more clearly. And it's also important that we see these stripes match well with the contour of drift period. On the background, so that suggests that this kind of structure is related to the drift structure, periodic motion. And further investigate the possible, these stripes, we found that these stripes are likely we can see that they span a wide energy range from several 100 keV all the way to over 1 MeV. So for this wide energy range, somehow it looks like they are they're likely simultaneously originated at. So the question is, what kind of mechanism can possibly create such high energy, wide energy range? This kind of disturb the energy spectrum simultaneously. So to further explore that, we turn to the test particle simulation. So here we simulate the gradient curvature drift of the particles in dipole field, and we just assume there's a short-lived down to dusk electric field, and it only lasts for about 6 minutes, and then we can see that when the electric field is there, then electrons on the night side will, due to the equal speed drift, will gain energy, and the electrons on the day side will lose energy. And after this electric field is gone, but the effects will persist and continue to evolve to this spiral shape structure. And then if we convert this test particle information to flux, we can see that similar zebra stripes to the measurements can be created just like this one. And then we further we look at another storm, and for this event on November 2023, and so this is the observation from Survey Reptile 2 at this time, indicated by the gray curve, the line, and then we a few hours before that we applied this kind of short-lived ad hoc electric field. So we assume there's only a EY component, and we assume the amplitude is really distance dependent, just like this, and it only exists for a few minutes. And by doing this, we can, in our test particle simulation, we can kind of recreate something similar to the observation. But the question is, this is kind of an ad hoc electric field, but is there any like more realistic and more physics-based electric field can explain this? So there's some hint in the onset time of this electric field, because if we take a look at the IMFBZ and EY, we can see that this the time when we apply this electric field seem to align closely to the southward turning of the IMF, so, which is based on previous studies, it's a kind of a sign of penetration electric field. So that raises another question for the future, that if the penetration electric field is the actual driver of these zebra stripes, and to address that, we are currently collaborating with Dr. Mariyama, who runs more physics-based electric field models, and we will further use that more realistic electric field and apply that to the test particle simulation to see if we can still see similar, very similar results as the measurement. So if the results is as expected, then that can be an interesting case showing that the rapid response of the ionosphere electric field to the solar wind is actually can leave some signatures in the inner magnetosphere or like in the radiation belt energy spectrum. So that's a summary of my slides, and I'll take questions. Thank you.
Thank you very much. Any questions? Okay, so the time is coming up. So yeah, let's move on to the last speaker, the organizer of the session, Luis.
Okay, thank you so much. So in this opportunity, I will talk to you about the impressive observations that we have obtained with the radar of ground-based instruments, interferometers in South America, and how these the neutral winds field actually compare with respect to observations from the Jicamarca Incoherent Scatter Radar at the equator, which is observing the equatorial vertical plasma electric fields. So just as an introduction, and I'm sure most people are familiar, at the equator, for example, we have it has been extensively studied the storm time behavior of the plasma drift in the vertical direction by the observations from the Jicamarca Incoherent Scatter Radar. This is in the left. This is an example of a very typical response of storm. Below in the solid line is what you would expect if there were no storm time effects, and the red squares show actually disturbances, departure from the quiet time baselines that are one of them actually immediately responds to the increments in the electrojet, which indicates an increment in the high latitude electric current system. And then another one that is not as obvious because there is no apparent effects in the AE index. But of course, we know that both of them are actually short time effects, actually boosted by different processes. This is, as I said, has been studied for a long time. This data, as you can see, from 1972, and based on about 20 years of observation, they have made out an empirical model of this, which is the Chillerson-Fayer model, 1997, which described basically the long-term effects in the vertical plasma rheostat equator, which corresponds to the wind action, what we call the disturbance electric field, that generate these disturbances that are anti-solar quiet time disturbances. Here on the right is actually an update of this same effect, but considering only 6 hours of continuous energy input using also the AE for a particular condition of solar flux of 150 units. In this case, each of these lines correspond to different energy input corresponding to 130 nanotesla and 300 nanoteslas, above the quiet time reference, which is about 130. So mostly the effects are in the post-main exerta, which is what Fayer and Shirless found a long time ago, but they didn't find any other effect in the solar local time, mostly because of the statistics bias. We did find that there is strong effects in the around sunset, which is a downward drift opposite to the upward drift, which will cancel the famous pre-reversal enhancement, which is an uplifting caused by the night-day transition, by the reversal of the winds in the upper atmosphere. But the main takeaway of this slide is that the disturbance dynamo electric fields that we see at least after 6 hours is actually anti-solar quiet time. And we'll see later that it's particularly important. Coming back to the observations that we will use just as a review, we'll have 4 operative systems that were working during the 2004 May storm. One at Hick America in the magnetic equator in the west coast of America, in Santarém in the east coast of South America, and Cachoeira and Leoncito, which are also interferometers and mid-latitude southern regions in the South American sector. And just as an introduction, what they do to measure the winds, as we have heard before, they basically use the red line, fixed nanometers lines argon lines to estimate the winds from the Doppler shift and broadening. From the broadening, we get the temperatures of the bulk motion of the dominant of the neutral dioxide atoms. This is here on the left is an example of what you can do when you have a network of this. It's very similar to what Marco, the instruments does, as Ryan indicated earlier, but we don't have like this anomalous imaging system because this is not Aurora, this is Serglo, so it's much weaker, the signal that we get. So we basically focus on point this at different locations, and from these points that you see here, we basically estimate the wind field data over a certain region if these sampling points are actually close enough. Okay, so these are actually the observations that we did in the main phase of the storm. During the main phase of the storm was characterized by, as long as we have the compression, right after this increment in the symmetric gauge, we have this strong upward drift as observed by the vertical, we have Hick America, and also a westward drift, which was also observed at Hick America. We used actually Gray's satellite drag observations, which show that this is exactly what the winds are doing. So it also shows that the coupling between the plasma and the drift at that particular region. And then later on, you can see that these effects at the equator are basically decreasing, and there is a remnant at the high latitude and the mid-latitude regions, and then eventually it basically goes to zero. Here, we have some effects that are mostly some of the literature of this particular storm has been shown that this is mostly related to penetration electric fields, some of them to substorms. But the winds, what they are doing at this time is basically also in the terms of the westward direction, the eastward direction, they're actually going to the west. So what we would expect is to be an eastward motion of the upper atmosphere, but it's actually going to the other direction. And this is exactly what we see. This explains why when we actually analyze the plasma, and this might be familiar to you because this was the famous very big expansion that happened during this storm, and you see that this is the actual anomaly, that instead of being about 20 north, 20 south, it's actually going down below because of the big expansion caused by the electric fields at the equator. And this, instead of going to the east, which what you generally would expect, is actually going to the west, just following and showing how there is a motion of control by the winds, which is also showing the same. Okay, and if we actually go deeper into what Hikamarka is showing, this is basically the same indices, the solar wind data we have here, the symmetric gauge, just to understand the different the stages of the storm. We have this the vertical plasma drift, the green line that you would expect, and these are deviations. But I would like you to focus your attention in this particular location. As we said before, this point here is basically more than 6 hours after the storm, after the onset of storm. And we will expect that this is actually, they will have an anti-solar quiet behavior, which is actually opposite. If this during the daytime should be westward, we're actually would expect to have an eastward or basically zero because it's daytime, but it's actually going more to the west. And the question is what happened here? Well, this is the same period of data when gold, if we go to the ON2 ratio, was showing this very strong vortex that we saw from the gold observations. This is consistent with what we see. So the idea is this actually, this might be an evidence that this is actually a disturbance. This ON2 ratio is mostly related to the disturbance wind that is also going to the equatorial regions, and that process is consistent. You have a high latitude energy input and generated this heating that is going to equatorial region. This is consistent with what we see from the gold observations, and this actually was so strong that reached the equatorial regions during the day. Generally, you have this dissipated way before it reaches lower latitudes because of the strong climate during the day. But it seems that the conditions were so that the expansion generated that there was no such same dissipation, that it reaches the equatorial regions and actually affected the electrodynamics at the equator. And this is exactly what we see. Well, just to follow up with analysis, what we did here is that gold has 4 of these sequences for this vortex that we show. And even though we don't have like observations that show that the winds is doing the same, some of the gray passes show that they are also showing a similar pattern, as possible as an indication that there is also a similar vortex in the winds if we were able to measure it. But the fact that whenever they reach to the equator, we saw like the same results indicate that there might be probably a similar vortex in the plasma as well. So what we did here, we just grabbed for this, we grabbed the contours of this just to understand the velocities. We wanted to see how fast they were going, if they were actually very close to what the plasma, equatorial zonal plasma was showing. we just focus on one particular point, which is this point that you see here, and basically we follow up that particular point, and we calculate it from there the velocities. So very simple, and then we compare that with the actual velocity showed by the drift. Well, they show to be very similar at the beginning of the day, and then they seem to get actually slower as they actually go to higher latitudes, at least these peaks, while the plasma still shows to be still stronger until it reverses to be. And during this period, there is also this behavior of shown by the grays wind. This is a cross-track wind, so it's basically in the zonal direction. It's basically showing a double peak that is also present every time we see this double pattern, this vortex arrive in the equator, which might be an indication that the wind was actually showing the same pattern and that the drift are probably also doing the same thing. And that's it. That's all what I want to show to you. Just to conclude, to summarize what we just found, that is how can we actually use ground-based and satellite observations to do all this analysis. And we compare the winds of the plasma drift are actually well coupled at different scales, but there are certainly, this is a very complex storm. I haven't talked about the big Y reversal that also seems to be affecting the westward motion. But we just don't have enough observations. We need really more observations. And that's it. Thank you. Thank you so much.
Thank you very much. Any questions? Okay, thank you very much, Luis, and thank you for all the speakers who participated and also stayed for the rest of the evening of the last day, and thank you for all the audience for staying here and participating in the discussion.